Welcome students, today's topic will be on Cartesian products and relations. In the last class, we started with the Cartesian product of two sets. In fact, we started with ordered pairs and used this ordered pairs to define the notion of Cartesian product of two sets, and finally, we ended up with the Cartesian product of two sets. Well, one can also define Cartesian product of n sets, but that is not the motive behind these lectures. Now, let us proceed with some more examples. We begin with an example or a problem. Let A equal to 1 2 3, B equal to 3 4 and C equal to 4 5 6. Let us find the following Cartesian products: A cross B intersection with C, second A cross B intersection with A cross C, third A cross B union C, and fourth A cross B union A cross C. Let us find the following sets. First one, we are given that A is 1 2 3, B is given that B is 3 4 and C is 4 5 and 6. Therefore, B intersection with C, the common element between them is exactly 4. Therefore, B intersection C is only 4. Now, A cross B intersection C is all possible ordered pairs from A and B intersection C. The first element from an ordered pair in A cross B or in A cross B intersection C, the first element should be from A and the second element should be from B intersection C. So, the first element is 1 4 and there is no other element in B intersection C. So, 2 4 3 4. This is A cross B intersection C. Now, let us try to calculate A cross B, which is, so B is 3 4, therefore, 1 3 and 1 4. Similarly, 2 3, 2 4, 3 3 and 3 4. This is A cross B. Now, let us try to calculate A cross C, and we know that C is 4 5 6. So, this is 1 4, 1 5, 1 6, 2 4, 2 5, 2 6, 3 4, 3 5 and the last element 3 6. Now, let us try to calculate A cross B intersection with A cross C. If you look back into what we wrote down for A cross B, then you will notice that elements of the form 3 4, 1 4, 2 4 are there. 1 4, 2 4 and 3 4. These are the elements that are common to both A cross B and A cross C, and in fact these are the only 3 elements. Fine. Now, notice the following fact: A cross B intersection C is equal to A cross B intersection with A cross C. Let us do the third one. We will have to calculate A cross B union C. So, the B that is given to us is 3 and 4, and C that is given to us is 4, 5 and 6. Therefore, B union C is 3, 4, 5 and 6, right. And A, what is given to us is just 1, 2, 3. Therefore, A cross B union C equal to the following ordered pairs 1, 3, 1, 4, 1, 5, 1, 6, 2, 3, 2, 4, 2, 5, 2, 6, 3, 3, 3, 4, 3, 5 and finally 3, 6. So, well, we all know that the number of elements in A cross B is going to be the number of elements in A times the number of elements in B. Now, the number of elements in A is 3 and the number of elements in B union C is 4. Therefore, the number of elements in A cross B union C is going to be 3 into 4, which is 12, and you can notice that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Therefore, we have not missed any element of A cross B union C. Now, let us try to calculate A cross B and B cross C and then take their union. A cross B is going to be, in fact, these two things were calculated earlier when we did the first one or the second one. So, A cross B and let me say that and B cross A cross C were calculated earlier, right. Now, let us just take their union A cross B union with A cross C. A cross B consists of 1 3, 1 4, 2 3, 2 4, 3 3, 3 4, while A cross C, the other one consisted of 1 4, which we have already returned, the other one 1 5, 1 6, and then the next one is 2 4, which we have already returned. So, we will have 2 5, 2 6, 3 4 is already returned. So, we will have 3 5 and 3 6. Now, again let us note the following, that A cross B union C is equal to A cross B union A cross C, right. Now, let us do one more problem or an example. So, let P equal to A, B and C. So, out of this P, let us form the set P cross P cross P. Let us form the Cartesian product of P with itself 3 times, which is a P cross P cross P. P cross P equal to A AAB, AAC, ABA, ABB, ABC, ACA, ACB, ACC, and then BAA, BAB, BAC, BBA, BBB, BBC, BCA, BCB, BCC, CAA, CAB, CAC, CBA, CBB, CBC, CCA, CCB, and the last one CCC. You can notice that this Cartesian product P cross P cross P is going to have, so the total number of elements in P cross P is going to be 27. Now, with all these things, let us move on to the next topic of what are known as relation. Now, yesterday we had some sets of the following form, all those ordered pairs x comma y such that x and y are real numbers, both are real numbers, and we had one more thing, what is known as x squared plus y squared is 1. What we found yesterday is that this set is not a Cartesian product of two sets, that is what we had, although this is a subset of R 2. Although this is a subset of R 2, of course, this is an example for a geometric object, the circle. This is not a, this set, although it contains ordered pairs, this is not a Cartesian product of two sets. So, this is not a Cartesian product of two sets, but this is just a product, this is just a subset of the Cartesian product R cross R. Well, let us look at one more thing. Suppose that A have got the following things, which is Ramu, Babu, Ramesh, Kumar and Siva. Let us have the, so A consists of 5 names of some people, someone. Let B denote the following names: Lakshmi, Manju, Mani and these three. If you look at the Cartesian product of these two sets, you will have 5 into 3, the totally a set consisting of 15 elements. But if I say that, just say that there is a relation between A and B, if A and B, an element of A is related to B if an element of A, for example small a, is related to B if they are married. So, let us write down this one. Let me just say R as the following things: Ramesh, Mani, second one Ramu, Manju, and finally Babu, Lakshmi. Right. So, in fact, how are these things done? Ramesh and Mani, they are married together. They both are married together, and similarly Ramu and Manju, they are married. And the last one Babu and Lakshmi, they are married. So, we are interested in the pair, we need some relation between two names or elements between two sets. So, let us make this formally, write it as a definition. Let A and B be any two non-empty sets, right. A relation R from A to B is a non-empty subset of A cross B. So, relation is just a non-empty subset of A cross B. So, natural question is how many relations are possible between A and B. We know that. So, let us make it as a remark, the number of elements of A cross B is same as number of elements of A times the number of elements of B. But when we are interested in the relations, which means we are interested in subsets of A cross B. So, the natural question is how many relations are possible between A and B. Put in other words, how many subsets of A cross B are possible. A is a set, is any set, any non-empty set then the number of possible subsets of A is 2 power the cardinality of A. This much is known to us, but if you look at the definition of the relation, it is defined as the non-empty subset, and one will have to always notice that the all possible subsets of A includes even the empty set. Therefore, the number of possible possible subsets, in fact I should say non-empty subsets of A cross B is 2 power the cardinality of A cross B minus 1. Therefore, the total number of possible relations between A and B is 2 power the cardinality of A cross B minus 1. So, this many relations are actually possible. So, the examples, in fact the examples that we gave, the first example which is exactly the circle, and the second example the natural possible one. So, two persons are related when they are husband and wife. These are examples for relations. Now, let us go with some more examples. Let A equal to 1, 2, 3, B equal to 2, 3, 4. So, first thing that one will have to observe is that notice that A cross B is itself a relation between A and B. So, this relation is called the universal relation. Right. In fact, for any two sets A and B, one can always define. So, A cross B makes sense, and therefore, this A cross B is what is known as the universal relation for any two sets A and B. A cross B is called the universal relation. Fine. Now, let us go back to the last example and then let us see. So, what we had is A equal to 1, 2, 3 and we had B as 2, 3, 4. Fine. Now, let us come up with a new relation or a subset of A cross B 1, 1, 1, 2, 1, 2, 1, 3, 2, 2, 2, 3, 3, 4. So, this is a subset of. Let us try to represent this pictorially. The first set have got 1, 2 and 3. Let us write down the second one, which is 2, 3 and 4. Let us look at the first one. The first element of the relation is 1 and 2. So, 1 is related to 2. So, let us draw an arrow diagram between 1 and 2. Second one is 1 and 3. So, let us again draw one more line. this time from 1 to 3, third one 2 2, fourth one 2 3, and fifth one 3 4. Right. Let us go back to the second example that we had in terms of names. Right, let us look at the second example again. We had A as Ramu, Babu, Ramesh, Kumar, and Siva. The second set B contains Lakshmi, Manju, and Mani, and the relation that we had are is Ramesh comma Mani, Ramu comma Manju, and Babu comma Lakshmi. Now, let us try to write this or represent this again in terms of pictorial diagram. Ramu, Babu, Ramesh, Kumar, Siva. On the other hand, we have Lakshmi, Manju, and Mani. So, Ramu is associated with Manju, is related to Manju, and Ramesh is associated to Mani, and finally, Babu with Lakshmi. These are the things. If you look at the previous examples, the two examples that we had, so in the second example, only very few elements are mapped to elements of the second set, few elements, only 3 elements of the first set or set A are mapped to or related to elements of B. Let us do one more example. A equal to 1, 2, 3, 4 and 5, and B minus 1, 0, 4, 9, 25. Now, let me define R as all those x comma y in A cross B with the given thing that y is equal to x square, right. So, now let us try to expand this and then see that whenever the element y, the second, whenever you have an ordered pair, the second element should be related to the first element by the condition that y should be of the form x square, which means the only possibilities are 2 comma 4, 3 comma 9 and 5 comma 25. Let us again try to pictorially represent this. One, 2, 3, 4 and 5, minus 1, 0, 4, 9 and 25. 2 is related to 4, 3 is related to 9 and 5 is related to 25, right. Now, if you look at this one, only very few elements of A are mapped to few elements of B, and so not all elements of A are mapped to all elements of B. So, few elements of A are left out, and similarly few elements of B are also left out. Let us have one more definition. Let A and B be two non-empty sets, and let R be a relation between A and B. Then the domain of R is the set of all first elements from the ordered pairs in R. The set B is called as the codomain of R, and the set of all second elements from the ordered pairs in R is called the range of R. Now, let us do one example. Let A equal to 1, 2, 3, 4, 5 and 6, and B equal to, sorry, we do not need any B. Here R is all those x comma y in A cross A, such that y equal to x plus 1. Fine. Now, let us write down explicitly what this R is. If you notice, our set A is 1, 2, 3, 4, 5 and 6, and our relation is all those ordered pairs x and x comma y, such that x is of the form or y is of the form x plus 1. And so, R is going to be 1 comma 2, 2 comma 3, 3 comma 4, 4 comma 5 and 5 comma 6. Now, let us write down, now let us try to draw the try to represent this pictorially. 1, 2, 3, 4, 5 and 6. 1, 2, 3, 4, 5 and 6. Now, let us try to represent 1 is related to 2, 2 is related to 3, 3 is related to 4, 4 is related to 5 and 5 is related to 6. So, now domain of R is going to be all first elements. So, which is going to be 1, 2, 3, 4 and 5, and codomain. So, all first elements, but you can notice that 6 is not related, and therefore, 6 is not going to be part of the domain. Codomain of R, it is the whole thing 1, 2, 3, 4, 5 and 6, while range of R is going to be 2, 3, 4, 5 and 6, right. You have the following. Let us look at one more example. A is going to be 4, 9, 10, 25 and B, this is similar to the previous example, minus 5, minus 3, minus 2, 1, 2, 3 and 5. Now, let me define R as all those ordered pairs x comma y in A cross B with the condition that x is the square of y or y square is x, that is what we want. So, let us try to write down all ordered pairs. Four comma minus 2, 4 comma 2, 9 comma minus 3, 9 comma 3, 25 comma minus 5 and 25 comma 5. Now, let us try to represent them pictorially. 4, 9, 10, 25, minus 5, minus 3, minus 2, 1, 2, 3 and 5. 4 is related to minus 2 as well as to 2, 9 is related to both 3 as well as 3 and 25 is related to 5 as well as to minus 5. Right. This is the diagram that we have. The first one represents the set A, while the second one represents the set B. Now, let us try to write down the domain, codomain and the range. Domain, look at domain of R, look at all the first elements of the ordered pairs that appear in R. The first elements are going to be 4, 9 and 25, while codomain of R is going to be, it is the whole of B which is minus 5, minus 3, minus 2, 1, 2, 3 and 5. Now, the range of R is going to be minus 2, in fact minus 3, minus 2, minus 5 and then you will have 2, 3 and 5. This is going to be the range of R. Now, let us look at the same example. So, now, if you look at this example, the number of elements of A is going to be is exactly 4 and the number of elements of B in this case is 7. Therefore, the number of elements in the Cartesian product is going to be 4 into 7 which is 28. Therefore, the number of possible relationships or relations from A to B is 2 power 28 minus 1. Well, this is going to be a huge number, but actually, the truth is this many number of relations are actually possible. Of course, we may not be able to write all these 2 power 28 minus 1 relations, but one should know that this many relations are actually possible. Let us do one more example. Let us consider the set of all natural numbers. And then define R as all those n comma m in cross n. Well, this n denotes the set of natural numbers. Let me write down on the top, n is the set of all natural numbers such that with the condition that m is of the form n plus 5. Right. So, if you look at this one, so first thing that you will have to notice that R is an infinite set. So, one can also write R as all those n comma n plus 5 with the condition that n is a natural number. Now, let us go to one more example. Let us restrict this subset R and then see some more, all those n comma m and n cross n with the condition that m equal to n plus 5 and n less than or equal to 4. N can be at most 4. Now, let us write down explicitly. So, now you should notice that this R dash is a finite set, and now let us try to write down this set. It is going to be 1. So, m is going to be n plus 5 1 comma 6 and then 2 comma 7 3 comma 8 4 comma 9. These are the only possible things that you have, right. So, by imposing conditions or by imposing more relations, you can notice that the subset that you are going to get is going to be smaller and smaller. The first relation, that just like saying that m is n plus 5, just by imposing a relation, what we had is an infinite set, but just by imposing one more condition like n less than or equal to 4, we are reduced to just a finite set, in fact a set with just 4 elements. Let us look at one more example. Let A equal to 1 2 3 5 and B is 4 6 and 9. Let me define R as all those x comma y in A cross B with the condition that the difference between x and y is an odd number. Right. Now, let us write down R in a more explicit form. Let us write down all the members of R. What we wanted is that the difference should be an odd number. Fine. Now, let us look at the first one. What we have is 1 minus 4, the difference 4 minus 1, the difference is just 3, which is an odd number. So, we will have 1 comma 4. 1 comma 6, the difference is 5. So, we have this 1 comma 9, the difference is 8. Therefore, this cannot be an element of R. Let us look at the second one, 2 comma 4, the difference 4 comma 4 minus 2 is 2, which is an even number. Therefore, cannot be part of R. So, 2 comma 6, the difference is 4, therefore, cannot be part of R. Similarly, now on the other hand, 2 comma 9, the difference is 7, and which is an odd number, therefore, it is part of this R. Now, the next one 3 comma 4, the difference is 1, which is an even number. So, we will have this 3 comma 6, the difference is 3 comma 9, the difference is 6, which is an even number, therefore, cannot be part of R. And then 5 comma 4, the difference is 1, 5 comma 6, the difference is 1, while 5 comma 9, the difference is 4 and cannot be part of R. Right. So, now once again let us try to represent this pictorially. This is our set A. On the other hand, we have the set B. Now, 1 is related to 4, 1 is related to 6, 2 is related to 9, 3 is related to 4, 3 is related to 6, 5 is related to 4, and finally, 5 is related to 6. So, these are the only relations that we have between the elements of A and the elements of B. Now, let us look at the same example, but instead of same set A 1, 2, 3, 5, instead of going to A cross B, the one more set, let us define the relation R on A, that is this relation R is going to be a subset of A cross A, R as all those x comma y in A cross A with the condition that the difference between x and y is an odd number. Right. Now, let us write down R explicitly once again. So, you will have this 1 comma 2, 1 comma 3, the difference is 2, therefore, cannot be, and similarly 1 comma 5, 2 comma 1, the difference is 1, 2 comma 3, the difference is 1, 2 comma 3, the difference is 3. Now, 3 comma 1, the difference is 2, therefore, cannot be part of R, 3 comma 2, the difference is 1, 3 comma 5, the difference is 2, therefore, cannot be part of R. Now, 5 comma 1, the difference is 4, 5 comma 2, the difference is 3, and 5 comma 3, the difference is 2, 5 comma 5, the difference is 0. Fine. Now, with all these things, now let us notice one thing in this. whenever you have, first thing that one can observe here is whenever the pair x comma y belongs to R, that immediately implies us that y comma x also belongs to R. So, let us use this example and then define the following thing. Let A be a non-empty set and let R be a relation on A. That means what? That is R is a non-empty subset of A cross A. We say that R is symmetric if x comma y belongs to R implies y comma x belongs to R, right. Whenever the pair x comma y is in R, the opposite pair y comma x is also in R. Such pair, such a relation is called as what is known as a symmetric relation. So, in the next class we will deal more with symmetric relations and we will give some more examples of relations, and we will also deal with the notion of what is known as the concept of a function. So, we will stop here. Thank you all.